And I'd like us to start with this problem. And this is in 2.8. So number 14 in 2.8. So let's read the problem. The graph shows how driving speed affects gas mileage. Fuel economy F is measured in miles per gallon, and speed V is measured in miles per hour. Miles per gallon, miles per hour. What is the meaning of the derivative f prime of v? So what does this mean?
What is the instantaneous rate? I'm sorry.
Very good. That's what it is. So so let me stop sharing. Instantaneous rate of change of f with respect to v. WRT with respect to v. That's it. So here's v. Here's f and here's v. Miles per gallon, miles per hour. So it represents the instantaneous rate of change of function v, f, with respect to the independent variable v. Awesome. Part B. Sketch the graph of f prime of v. We'll do that. Let's do it right now. Let's do it. So I did not print out this, but I would like to print it out. It's easier if I just do a... So give me 1 second. It should be better. It doesn't allow... Yes, of course. So I am going to print it out right now. It will be easier than me graphing it. Okay. And we will graph the first derivative, or the rate of change of f with respect to v. Good. So that will be our second question. And third question is, at what speed should you drive if you want to save on gas? And we will see this in a minute on the graph. Here it is. Perfect. So I'm going to make this page 6. Okay. So in order to graph the derivative, exactly underneath, it's like it's a continuation of the vertical, or I'm sorry, of the y-axis. For each and every point, I should determine, I will not do it for each and every point, of course. So this will be f prime, and this will be v. So I'm going to select few points, like, for example, for 10 miles an hour, for 20 miles an hour, let's say for 40 miles an hour, let's say for 60 miles an hour, maybe even for 50. So I'm making sure that I put these points here, 10, 20, 40, right under the each 40 under the other 40, and 60 and 50, and so on and so forth. So this is 10, 20, 40, 50, and 60. Like we did last time, I have to estimate. I don't even have grid, so I have to estimate the slope here, 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 and so on and so forth. I'm going to use a different color. Obviously, right here it appears to be 0. The slope appears to be 0. Okay, fine. Right here, the slope appears to be negative. So it goes below the x-axis. So I'm going to say maybe 1/2. So somewhere here. For this one, maybe it's just small positive right here. For this one, it's bigger positive. So something like, I don't know, 3/1, maybe a 3. What about here? Much bigger. I don't know, like 4/1 maybe. So notice that the rate of change is positive till it's 0, and then it's negative. One more time, the slope of the tangent here, then the slope of the tangent here, then the slope of the tangent here, then the slope at here where it's 0, and then negative. These are the numbers that I will plot, exactly how you see it here. So something like this. Is it exact? Oh no, absolutely not. It's not exact. I estimated everything. But it's clear that here it's much higher, here's much smaller, and then smaller, and then 0, and then it becomes negative. That's why it goes under the x-axis. So from all these situations, what do you think will be answer to question number 3? At what speed should you drive if you want to save on gas? What will be the best from the graph?
10 miles an hour.
Here, the rate of change of gas in miles per gallon, right? So here, the rate of change is huge. In order to drive at 10 miles an hour, we spend a lot on gas. In order to drive at 20 miles an hour, we spend a little bit less. The rate of change is smaller. To drive at 40 is even less than when we drive at 20. So it appears that at 50 is the best gas mileage that we can ever get. And it makes sense. Say it again.
What's going on at 60 miles an hour?
So at 60 miles an hour, it appears that it goes the other way. In other words, we're gaining gas, but that's not possible, right? So this is the best. So here, I can't say that the rate of change is negative. I mean, I can't really envision that. But obviously, and they also tell us, right? So always try to drive at the top, at the middle of the odometer, right? So the 50 will be always the best, the easiest, the best gas mileage.
So was this a good example of the difference between the theoretical and the physical?
So I see I see this example. You're right. So, but obviously at 60, and we know that it's absolutely true that if you drive 70 miles an hour or you drive 60 miles an hour, miles per hour and 90 miles an hour, where am I trying to write here? So miles per hour, of course, you're using more gas. The higher the speed after a certain moment in time, the higher the speed, the more gallons of gas you use. So that is known. Just to try it. Try to drive at 70 miles an hour for a day, and you're going to see that if you drive at 50, you're going to cover a much smaller distance than at 50. So we know that. How they came up with this piece of the graph, I'm not sure. Because you can't say that you're earning gas if you drive at 60, right? Good. Measurement unit, by the way. So they're not asking us for the measurement unit, but this is extremely important. So what is the measurement unit? So we know that F is measured in miles per gallon. We know that the velocity is in miles per hour. So what will be f prime measured in? And remember, it has to have two measurement units. It has to have the measurement unit coming from the y variable over the measurement unit coming from the x variable. So this must be miles per gallon, and this must be miles per hour. It's always the case. It's a ratio. So this is the rate of change of this with respect to this. So this is the variable from the y, the measurement unit from the y variable, and this is the measurement unit for the x variable, always and forever. Okay. Do you need any explanation about the discussion, or we can continue with other problems? Anyone needs anything on that? Now, please understand how we graph the derivative, right? For each point, we have to estimate the tangent, the slope of the tangent line. Okay, I like this graph. I don't know if I can find it. It's on page 154. So let me see if I can put 154 in here. I'm going to put 154. And I'd like to show you that graph. And then we'll continue 154. 54. Enter. Why? Yes. Okay. So this was the graph that I wanted you to look at. I wanted to see that the right-hand side. Oh, what it did, it jumped, I think. It jumped from one. So here is what I wanted to show you, even maybe easier to understand. So here the slope of the tangent is negative. Here the slope is 0. That's why the derivative has to cross the x-axis, because the slope of this tangent is 0. Here the slope is negative. That's why right here it's just this number, -1. Here is 0. Here, so now the slope starts increasing, and at this point is the maximum possible, because then it levels off again. So that's why this is the peak of the rate of change. And then it starts leveling off, and I don't understand why it doesn't allow me to open it to the side. But I wanted you to see that graph. And now I wanted to go back to 2.7. Please close. Okay. It had a delay. Okay, so I wanted to look at, okay, that's enough. Okay. So I wanted to look at displacement, something called displacement. I wanted to look at some velocity situation, maybe. So let's browse through to illustrate with other examples. I want to discuss something like this. Find an equation of the tangent line to the curve at the given point. So that's the first thing that I would like to continue with. So let's take a look. Any preference? We had an example with a rational function a minute ago. Let's look at an example with a quadratic function. We did that too. And we also looked at an example with a radical function. Is the quadratic okay? You prefer something else? Anyone?
That's good.
Okay. So then we have y equals 2x squared minus 5x plus 1. And they're giving us a point. And they're asking us, okay, find the equation of the tangent line to the graph of this function at this point. Of course, this is a quadratic function, so we will have a minimum. I have no idea where 3.4 is. I'm not graphing the function, but let's say here is 3.4. So they're asking us to determine the equation of the line, of the tangent line, to the graph of y at this point. So I have a point, and I know an equation. Can anyone give us the equation that has a point and a slope? Can anyone give us the equation of a point slope form from algebra?
So y2 minus y1.
No, that's the y minus y1 equals the slope times x minus x1. You're correct with the other one, y2 minus y1 over x2 minus x1. That is the slope. That's good. But we want this one. We have 3, 4. 3, 4. How do I determine the slope? Can anyone give us an idea how to determine the slope of this line, of the tangent line?
Y and X.
Say that again.
Well, I would start by having something for Y and X.
No. How do we find the slope of the tangent line to the graph of y?
Isn't the derivative?
Yes, of course. It's f prime evaluated at 3. This is the slope, of course. That's why we are studying this. We could not determine the slope of this line with algebra, but now we know how to determine it. We needed 2 points. But there is no other point that the function goes through. This is a tangent. It's not a secant. If I want to determine the secant that passes through 2 points, I can. But this is not what we are asked to determine. Awesome. So now let's find f prime of x first. Or we can directly find f prime of 3 using the other definition. So a few minutes ago, I explained the fact that in this case, we're not really asked to find f prime of x. We can find f prime of x and then plug in a in it. That's fine. But this time, let's use this definition. Although for this function, to be honest, this would be easier than this. Maybe. It's up to you. What would you like to illustrate with? And we'll do it. You choose.